Aí você pode começar.
Tá, em inglês, né? Okay, so I'm going to present today this paper from the Harosh group from Paris. It's a paper from 1999 called Seeing a Single Photon Without Destroying It. Okay, so basically what it does is that until then, light detection was usually a destructive measurement. So you had a detector that annihilated the photon and converted it into electrical energy. So therefore, you could not measure the same photon twice. It was impossible because the photon did not exist after the measurement. So what this paper proposed was the first quantum non-demolition strategy to measure a single photon. So then you could measure the same photon as many times as you could experimentally do. For this, they required some extremely strong, so sorry, there is a typo here, some extremely strong matter radiation coupling. And it was achieved through cavity quantum electrodynamics. And this whole experiment, both the theoretical and experimental part, was so relevant that Serge Harosh divided the Nobel Prize, the 2012 Nobel Prize, with this American physicist here that did some similar experiment of non-demolition measurements. So usually until then, in quantum non-demolition strategies, you had a meter radiation beam, and it was divided into two halves. One half was unaltered, so it was just for reference, and the other half was coupled to a signal beam in some nonlinear medium, and then it had some refraction and a phase shift. And at the end, through interferometry, this phase shift was measured. So between the reference beam, unaltered reference beam, and this coupled beam. So here in this particular experiment, what they actually used for the meter beam was a single atom, and the signal beam were the modes of a cavity C. It was a pure state, ideally just a single mode, and the coupling occurred when this atom crossed this cavity C. So this atom could be in three possible energy levels. So there was a ground level, G, an excited level, E, and a reference level, I. So inside the cavity, this mode was resonant with the transition between the ground level and the excited level, but it was not resonant with some reference level transition. So if the atom entered in this I level, nothing would happen. So if the atom entered the cavity at time equals 0, it would undergo a reversible Rabi oscillation of this kind. So if the atom enters at the ground level, it would have so the atom so the cavity has one photon. Just for the example here, the cavity has one photon inside of it, and the atom enters it at the ground level. So it undergoes this Rabi oscillation here. So there's a superposition of the system state of the atom at the ground level and one photon inside the cavity, or the atom absorbs the photon and there is no photon inside the cavity. If we set the interaction time to be perfectly 2 pi over the Rabi frequency, what we have at the end is only this part here. So at the end, we still have necessarily one photon inside the cavity, so nothing changes there, but the whole system gains pi phase shift. So it has this minus sign here. Okay, so how do we measure it? If we put superposition, the atom enters the cavity in some superposition state between the reference level and the ground level. If there is one photon, the reference level part does not change, but the ground level part changes. It acquires this minus sign here. And if there is no photon inside the cavity, of course, nothing happens. So it leaves the cavity exactly as before. So in short, the atomic coherence changes the phase shift of the atom if there is one photon inside of the cavity, but it does not destroy the photon. The photon is still there at the end. So you can see here that the initial system state there is one photon, and here still one photon. Here no photon, and still no photon on the other side. So to measure it, they used Ramsey interferometry. So you had some auxiliary field R1 of frequency E, and this frequency was close to the resonant frequency between the ground level and the reference level transition. So here, if it's exactly the transition frequency, if we start with the atom at the ground level, this superposition is the final state after the auxiliary field, and if we start at the reference level, this happens. So there's a diagram. So just to clarify here, so this is the atom, and it undergoes firstly this auxiliary field here, then it enters the cavity, then it goes through another field, and then it leaves the cavity and is detected by some detector. Okay, so what the whole system does, if we start with the meter in G. So we don't know if there is a photon inside the cavity. There is this probably. It goes through the first reference field, auxiliary field, and we have this. The ground level turns into this. Then it goes through the cavity, and the part that is coupled to the no photon part, nothing happens, but the part that is coupled to the photon part, it acquires this minus sign. And then it goes through the same auxiliary field here. And in the end, you can see that there's at least theoretically, a perfect correlation between nothing have photons and the final state of the atom being the reference field at the reference level, sorry, and having one photon inside the cavity and the final state of the atom being at the ground level. This, just a side note, was what I said, that there is not an agreement between the book from Milburn and Weisman and the paper, because they define this second field as the opposite of R1 and not as the same thing. So there's a inverse correlation here. You should change these two things. So okay, there's and at least theoretically, if you measure the atom after it leaves the cavity, you know with perfect certainty whether there is a photon inside the cavity. And this is important, if there was a photon and if there still is a photon inside the cavity, because it remains unchanged. Okay, so this was the diagram I showed before. Actually, it's not exactly like this, because it's not like there is a constant field here, a constant field here, another field inside. In the middle of them, they turn this on, and they turn this on. Finally, they turn this on. And this detector detects whether in which level the atom is after it goes through the cavity. So here, the first image is if this section B here is if there is no photon inside the cavity. So this is the quantum trajectories the atom goes through. And you can see here is the graph of the probability of finding the atom at the level G at the end of this whole measurement. And here you vary this frequency of the two auxiliary fields R's. And you can see that the probability changes, because then the distribution between the part that is at the auxiliary reference field and the part that is at the ground, reference level, and the part at the ground level, they change. So there is this graph here, here, and you can see that if there is an atom, there is a photon inside the cavity, the whole graph shifts by pi here. So this dotted line, the dotted gray line, is graph here, and you can see that everything is shifted. Okay, so the setup for the actual experiment, they used a rubidium atom in the reed bag. There's a typo here, circular state. The ground level had a principal quantum number of 50, the excited level of 51, and the reference level of 49. So these were the frequencies of the transition, the resonant frequency of, the frequency of the resonant frequency of the transitions between the levels. The atom was emitted in pulses of on average 30 or 60% of atoms. So half of them had some atom inside of them. And then they could measure the atom position with enough precision of 1 millimeter. The detectors at the end had 30% efficiency, and the cavity was made of neodymium spherical mirrors, and it was cooled down to almost 0 Kelvin. So there was a very strong probability of not having any photon inside the cavity at the beginning of the experiment. And the photon decay time inside the cavity, after set everything up, they had also a electrical field going through the cavity. So for the resonance to, I don't remember now exactly why they had the field, but anyway, the decay time inside the cavity was 1 millisecond. This was way longer than all the measurements they did. They were in the scale of microseconds. And the Rabi frequency of the transition inside the cavity was this one. So, okay, well, the actual experiment consisted of emitting firstly an excited source atom. So the same thing, but instead of entering in the ground level, it entered the system in the excited level. So it went through the Rabi oscillation, and they did not know whether it would leave the cavity as an excited atom, and if it left the cavity as an excited atom, the cavity was empty of photons, but it could leave the cavity as a in the ground level. Then in this case, it would have left a photon inside the cavity. So the probabilities of leaving no photon was of 77%, and of leaving one photon was of 18%, and there was also a negligible probability of leaving more than one. Sorry, just a second. So they send this first atom, it goes through the cavity, it is measured at the end, and then they send a second atom at the ground level, and this second one is the meter. It has some residual probability of actually absorbing the photon and messing up with the whole experiment. But if everything goes well, it will leave the cavity at the ground level. So the photon is, if there was a photon inside the cavity, it's still there. And what they measure is the probability of this atom being at the ground state, given that it was the first atom, the source atom, was excited. So the probability of it being in the ground state, given that there is no photon inside the cavity, and the probability of it being in the ground state, given that there is one photon inside the cavity. So the source atom released one photon inside the cavity. Each measurement was repeated 2050 times. And then what you actually want is knowing the probability of having one photon inside the cavity, given that, so here, if you had the meter atom at the ground level or at the reference level. just to remember that if you had here the atom at the meter atom at the ground level, this means that there is a photon inside the cavity. So they vary the frequency of the auxiliary fields, and this is the graph they got. So just to explain this, here, if the frequency of the resonant field is exactly the transition rate between the reference level and the ground level. So we had what we discussed before here, and we had this. So a complete, absolute correlation between the final state in the reference level with no photons and in the ground level if one photon. So if you go back here, if it has no photons inside of it here, so minimum probability of finding the atom at the ground state. If there is one photon inside the cavity, maximum probability of finding the atom, the meter atom at the ground state. And these two lines here, the dotted line and the straight line here, the continuous line, they were numerical simulations considering all the possible sources of error, and you can clearly see that they fit very well the actual experiment. So all the sources of errors mean that it's not going from 0% to 100%, of course. So now they try to do a third measurement of whether there is a photon inside the cavity. The first one done by the source, first meter atom, and now they send a second meter atom, and they measure the probability. No, sorry, they send now a second meter atom, but this time it will absorb the photon if there is one photon inside still one photon inside the cavity. So they measure the probability of it leaving in the excited state. This means that it has absorbed this photon that is still inside the cavity, given that it was in the ground state. So there was actually a photon inside the cavity, and the same thing if it was in the reference state. So there was no photon inside the cavity in the zero difference that we discussed here. So here, if Ni is exactly the transition rate. So this is what they measured. Here is, given that you don't know the result of the first measurement, so you can clearly see that now, going back to the zero here, you can clearly see that the probability of finding one photon, given that you have already found one photon, is higher than the probability of simply finding a photon. And the probability of not finding a photon, given that you have already not found a photon, is lower than of finding a photon. So clearly you are measuring the same thing twice. And okay, so this was it basically. And so they did it measuring it with more meter atoms, and it yields some similar results, but of course with more source of errors. And they also said that it was theoretically possible to do the same thing for multiple levels, multiple photons inside the atom, but you have to have some very precise measurement of the phase shifts that weren't just this here, like pi phase shift here, but some more complex stuff. So they did not have the experiment capabilities at the time to do it, but they had the intention, and I actually did not look up if they actually did it afterwards, but it was theoretically possible at least. So this was it. This was the whole paper. It's actually very simple to read. There's one simple equation, the whole paper. And yeah, any questions?
I have a question.
Okay.
Do you know this other guy that shared the Nobel Prize? The experiment was to measure more or less the same thing?
I actually don't know.
Okay.
It was not the same experiment. He was not part of the group, but I'm not sure with what he actually did. I just looked the first paragraph of the Wikipedia. Okay. He was not involved in this experiment.
More questions?
I have a question, Lui. It's just to be sure if I understood it. So the last plot you showed, I think it was like conditional probability. Yeah, this one here. It's just to be sure that you're like actually measuring the same photon twice. So that's why you make this sequential measurement.
Sorry. So
the motivation.
yeah, here they are actually measuring the photon twice, because the first time you are indirectly measuring the photon because you are just looking at the source atom after it released it, and you expect that it released the photon inside the cavity, but you are not actually interacting with this photon inside the cavity. So here they are actually interacting with the same photon twice. This first time with the emitter, and it does not destroy it, and the second atom that absorbs it if there is something to absorb. And they did it so sending multiple meters also that do not destroy the photon, but of course then things get messier because each meter has actually I put here where is it? Oh, here. So each meter has actually a 20% probability of actually absorbing the photon and messing up everything. So if we start to send multiple meters, then everything gets messier.
I see. Thanks, Lui.
More questions?